Beautiful, and we are live, ready to go. Guys and gals, welcome into the chat. Welcome to another Dr. Drew live stream. Let's just wait a few minutes for folks to chime in to the chat here. And go ahead and get started. Just gonna go ahead and do some dyings, some quick dyings real quick before we jump into it. I'm gonna start off with conjugated dyings and go over some of the reactions that we might have seen. Okay, you're going to see these in Organic Chemistry 1, Organic Chemistry 2. I know some folks are doing alcohols today. There we go. Hello, welcome into the chat. Guys, anyone that's new here, my name is Drew. Go live every single week to answer your STEM questions. And one sec, chat. I want to get these problems up for today. And perfect. There we go. So now we got these problems up and open for everyone to see. And perfect. Just check the audio real quick. And we are good to go. Perfect. Okay. Just pulling up some examples real quick here. Bear with me one sec as we jump into it. Fran, welcome into the chat. Okay. So we're going to have these dienes here. All right. We're going to have these dienes. Solo Mia, welcome in. I'm going to draw out this compound like this. Okay. Compared to Sanjo, Solomia, Big Vert, welcome in. Guys, how's everyone doing? My name is Dr. Drew. Let me know if you're new here by commenting the word new. Oh, my mic is overlapping. Hold on a sec, chat. Thank you for that, Fran. Appreciate you. Okay, Solomia says IR spectroscopy. All right, got you. Got you. Are you currently taking OChem? Hold on, chat. Let me fix the mic real quick. Wait, you said it's overlapping? What do you mean by that? I only see one audio. Okay. So IR spec, perfect. We're gonna jump right into that. Let me just check the audio real quick. Guys, anyone that's new into the chat, welcome in. My name is Dr. Drew. I go live every single week, Monday through Thursday, to answer your STEM questions. Today we're going over OChem. Let me just check the audio real quick. Really? It's repeated twice? So far I don't hear anything. All right, I'll keep that open. Leslie, good to see you. How's it going? All right, so first topic we're going to go over is going to actually be IR spec. Okay. So IR spec is going to be infrared spectroscopy. And so my question for you y'all is, what is something that is confusing about IR spec? Is it how to read the graphs? Is it how to identify the peaks? Is it going to be the signal characteristics? For example, the wave number. Okay? Yeah, absolutely. Grignard Reactions will be up next if you stick around. I'm going over first come, first serve. Okay? You effectively have to go over and identify the different wave numbers. So, let me give you some examples of what you might see. For instance, this one over here might look something like this. So the peak is coming down. Might look something like this. Go down kind of like that. Okay. And then this number over here is going to correspond to the wave number. So guys, we're going over IR spec. Okay. So this is for an alkane. And then the wave number here is going to be wave number. This is going to be in inverse centimeters. Leslie, thank you for the follow. And, okay, so the wave number here for an alkane might be indicative of this region here at 3200 inverse centimeters here. That's going to be the wave number. Guys, welcome into the chat. My name is Dr. Drew. Comment the word new if you've never been here before. Guys, we're going over organic chemistry at the moment, but you can comment down below what question you guys want to go over next. And then we have Grignard Reactions. So we can see that this peak is for an sp3. So this is going to be for CCH. And then guys, let me know if there's any problems with the audio. Someone said that there's some problems with the audio, so just let me know. Karina, thank you for the follow. And then, so this is just going to be one example for our alkane peak. Might look something like this. And then another alkene. So ENE, alkene, that means what? What's the difference between an alkene and an alkane? Comment down below. So alkene might look something a little like this. I'm going to draw this peak. Might be a stretch downwards like that. Okay. All right. And then so this peak over here might correspond to a C double C bond just like this. So this is a C double C bond, which once again, this peak down over here is going to correspond to the wave number. So the wave number is in inverse centimeters. And sometimes people ask me, Drew, do you have to memorize? And it's kind of like, yeah, you have to memorize, but I don't suggest memorizing the numbers per se. Rather, I suggest you do practice problems. So what do I mean by that? I just mean don't memorize the numbers per se. I just want you to start to identify, kind of like a detective would see the fingerprints and match what that might look like. Stella, welcome in. Guys, anyone that's new here, comment the word new if you've never been to a live stream with me before. If you've never been here before, comment the word new so I know you're new. We're currently going over organic chemistry in the context of IR Spec. And my name is Dr. Drew, PhD in chemical engineering. And the last one we might have here is going to be alkyne. All right. Alkyne is going to be basically, we'll have one peak just like that. And this peak is going to go all the way down over here, just like that as well. Okay. So alkyne is going to live over here. This is going to be below 3200. This is going to be a C triple bond to an H here. So that's going to be an alkyne region over here. All right. And then this one's going to be, wait, let me make sure you guys can see that. Yeah, I think you guys can see that, right? And our alkane over here as well. So that's going to be our next group. So once again, now this time, notice that this peak is going to come down to about 3,000 this time. So it's going to be about 3,000. So the moral of the story is, the end of the movie was basically, if you see something to the right of 3200, okay, anything to the right of 3200, whoops, anything to the right of 3200 gonna look like a alkane. Whoa, got 100 on the fluids. Good job, Jackson. What was on the quiz? Okay, anything to the right of 3200 gonna be an alkane. And then anything to the left, directly to the left at 3000 is going to likely be an alkene double bond. Anything to the left of 3000 way over here is going to be a single little peak. That's likely going to be an alkyne. Alkyne is triple bond. Good evening, Isaac. I'm chilling, brother. How are you? Guys, shouts out Isaac. Isaac, remind me one more time. I think you're a physicist, right? I think you're a physics... I know you're a physicist, or like, was it electrical? Bro, I'm sorry, I forgot. Yeah, good question. The question is why, and the reason for this is, well, because of physics. This is modeled by Hooke's law. Okay, so if you're into physics, this is essentially physics. This is basically Hooke's law. But for anyone that's taking organic chemistry, don't worry too much about why. Try to just understand what are the signals going to be. Okay, of course, there are going to be some exceptions. So let me give you some exceptions over here. So the exceptions here are going to be if we have sp2 bond, for instance, C double bond C with 4 R groups. Doesn't matter if they're unique or not, as long as they're R groups, as well as R, C, triple bond C, R. Okay, these are exceptions here. These are going to be no signal. Okay, so the person that asked about IR. Let me know if this is making sense here, if you have any follow-up questions. And yeah, my first tip for you is to try to memorize. Again, don't memorize randomly per se, arbitrarily. I want you to focus on understanding, you know, what are the characteristic peaks by doing a lot of problems. So it's going to have no SP2 character, okay? And it's going to have no SP character for H. Notice that these are all occupied, all right? Leslie says, never learned this. Leslie, we're going over organic chemistry. Are you currently taking OChem or Gen Chem? And cool, next, let me know if this is helpful. And guys, I'm going to start to write down the request. Basically, first come, first serve. Anyone that's new here, I'm Dr. Drew. I go live every single week to answer your STEM questions. The next topic I saw was Grignard, and then, yeah, Kenya. Kenya, I'm going to get you down next as well. Okay, Solimia, there you are. So Grignard, and then basically I saw, what was it, resonance? Resonance? I think I saw resonance, guys. Okay. And guys, if I miss your question, remember this is first come, first serve. Just stick around. I can go one at a time. Right now we're going over OChem, but remember I can do math, Gen Chem, OChem, physics. Springs are even symbolizingly great systems. Okay. To learn potential energy and stored energy in physics. Okay, which of the following gives rise to a prominent peak in the mass spec with mass Z of 91? So Lamia, can you drop a screenshot? Can you send me a screenshot either on TikTok or IG, and then I'll take a look. Kenya, thank you for the follow. Kenya, I think you're next. Okay, also NMR. So then King says NMR. Perfect, guys. Keep the questions coming. It's just going to be first come, first serve. So good luck, Jackson. Yeah, good luck. And then, so the person that asked about Grignard, let me know if you're here. Thank you, thank you. The person that asked about Grignard, let me know if you're here, because you're going to be up next if you want to go over Grignard. And then Solomia, I have your question too. So I'm going to just take a screenshot of your question, and I want to see what are the choices here. If you can send me a screenshot, that would be best. Okay, so the person that asked about Grignard, and then resonance, and then King asked about NMR. Let me know if you guys are here. Guys, we're basically going over one at a time. So this one was for quick introduction to IR. Ionization and peak bonding energy. Okay. So the person that asked about Grignard, are you still here? If not, I'm going to skip you. Person that asked about resonance. Okay, XO. XO, perfect. So, guys, keep your questions coming. If I skip you, I do apologize. Just let me know. I'm going to go back and forth. So next topic now, guys, is going to be Grignard. Okay? So same question for you. What is confusing about Grignard? Do you want to go over the reactions? Do you want to go over practice problems? Do you want to go over theory or just a general overview? Okay? So now we're going to go into Grignard reactions here, guys. And for example, I'm just going to pull up some examples here. Okay, bear with me one sec as I pull these up real quick. Okay, Grignard is for preparation of alcohols, okay? So it's spelled Grignard, okay? Yeah, Divya, lock in, my friend, lock in. So Grignard is going to be for preparing our, it could be between an alkyl halide and alkyl and magnesium. So we're going to have an alkyl halide, Rx. This is going to be an alkyl halide, right? And guys, this is going to be in terms of using magnesium. We're going to prepare RMGX. Okay, so this is going to be what's called the Grignard reagent, right? Let me know if this is making sense here, guys. Do me a favor and drop a thumbs up if you're understanding so far about Grignard reagents. All I'm doing is preparing an alkyl halide, mixing it with, magnesium, and then going to generate our Grignard reagent, okay? So it doesn't matter what R is. That's the beauty of this reaction. As long as we have any R group, we can replace that with our alkyl halide, right? Okay. All right, BDR, I'm going to check the channel right now. So if we have two equivalents of Grignard, are we inserting the reactant twice? Yes. If you have two equivalents, then you're going to basically do that multiple times, depending on how many times. So let's just do that between a ketone. Okay, let's just do a quick little mechanism breakdown between that and a ketone. Okay, and guys, we're getting some more requests today. So once again, if I skip you, it's not intentional. It's just trying to just keep track of the chat and be fair to everyone. Seems like lots of folks are going with organic chemistry today. And so guys, if you're taking OChem currently, comment the word me. Okay, comment the word me if you're currently taking organic chemistry this semester, just so I know. Okay, and comment down your major down below. What's your major if you're currently taking any STEM classes? All right, so first things first, we're going to do a nucleophilic attack. So suppose we have a ketone, anything on the left hand side right over here, this is RC double bond O, or okay, that's going to be called a ketone. A ketone reaction is going to generate that first compound here, and we're going to have R O minus, okay, just like that, R and then R. Okay, all right, and then you said ester after? Absolutely. Okay, got you. Okay, and then now the next thing is going to be proton transfer. So I'm going to add water. So I'm going to protonate what? I'm going to protonate my oxygen here. Okay, and then that's going to be the next one here. Okay, Kenia says organic chem, bio major. Thank you for that. King says me, so King's currently taking organic chemistry. Thank you, King. Okay, and guys, my name is Dr. Drew. So once again, anyone that's new here, I do go live every single week, Monday through Thursday, to answer your STEM questions. And then perfect. So now we've formed our alcohol. So what is Grignard for? It's to create alcohols. Okay. So it doesn't matter what the R is here. Now let's suppose that I have, an ester. Let me see if I have a good example here. Yes. Grignard reagents can also be reacted with esters to produce alcohols. But the only difference is we're going to have two R groups here. Okay. Physics, chem, and bio. Beautiful. Good luck with that, everyone. So suppose now I have an ester. Okay. Before moving on to the ester example, guys, do me another favor if this mechanism so far is making sense. Okay, drop a thumbs up if we're so far so good here with the Grignard mechanism. Again, we have a ketone, okay, reacting with via nucleophilic attack to create an alcohol. Here is on the right hand side. So every time you think of Grignard, just think about alcohols. All right. Okay, beautiful. So I'm going to go ahead and move on. If I went a little too fast for you, just comment that crying emoji, and I'll go back to re-explain. Don't be afraid to ask any questions. And then here we have an ester. So how do I know it's an ester? Because we have the formula R, C, double bond O, O, R. So this is an ester here. Okay, and so what if we use Grignard? Okay, I'm going to give you an example where we do Grignard, and then we're going to have excess. So some professors say two equivalents. Some professors write the word excess. Me personally, I like to write the letters X and then S. That indicates we have excess CH3 MgBr. And look, here's where I know I have Grignard. So the trick I like to say is that the letter G is in Grignard, and then I have Mg. So if you see Mg, that's a hint that it's going to be Grignard. Does that make sense? The word Grignard has a G in it, and so does magnesium. So that's how I know I have a Grignard reagent here. And then next I'm going to have excess H2O. So last time we said that we have an alcohol here, and then we replace one R group. But this time we have excess. So I'm going to go ahead and draw the product, and then chat, go ahead and take a second here to draw the product. Okay? So EXO, let me know what EXO says. Oh, okay. Guys, that's why I have my O Chem group course. I like to call it the O Chem group course because after working with me, you're going to say O, okay? And you're going to feel like you understand it more. So EXO, what is the product here, my friend? Hopefully this is making sense. Okay, so the product here, EXO said O, and then we're going to go 1, 2, 3, 4. We have OMe, okay, and we have OH, but we have excess, okay? So actually, rather than OMe, we're going to have methyl CH3 and methyl CH3. Why? Because we had excess. Let me highlight that for you, chat. Sometimes people don't like the colors, and then sometimes the colors make it click for people. So I'm gonna highlight this part in blue, and then I'm gonna highlight this part in red here. So the CH3 is because we have excess CH3 MGBR. Okay, you might say, hey, what happened to the MGBR? Well, it formed a byproduct. We're gonna have MEOH as the byproduct. Okay, XO, let me know if that made sense. Guys, once again, do me a favor and drop a thumbs up if this made sense so far. We're going over Grignard reactions currently on organic chemistry. BDR, I know you asked a question, so you're gonna be up soon. I'm gonna add you to the list. And then guys, if at any point I lost you or you got confused, just comment that crying emoji. Let me know if you got confused at any point. Okay, so I'm gonna cross you off for now, XO. But if you stick around and you ask another question, just stick around, and then what do you call it? Like, I'll be sure to keep it going for you. Okay. So guys, it's pretty much first come, first serve. The next person that asked was resonance. So if you asked about resonance, let me know if you're still here. Otherwise, King, you're going to be up next for NMR. And then also, Salomia asked about mass spec as well. And then BDR. I'm going to check the Discord. Beautiful, guys. Guys, just want to let you know that my name is Dr. Drew. All right, thank you, Salomia. And guys, I just want to let you know that I have a website up on my link in bio. It's called engineeringminds.co. So you can tap that link in bio or go to engineeringminds.co. And guys, this is going to be like your basically your go-to STEM study resources here. So we have the Discord, which is 100% free. We have free resources for math, gen chem, ochem, physics. And lastly, we have tutoring available. So if you're taking math, including calculus, you're taking physics, you're feeling cooked for organic chemistry, guys, sign up for a call. First session is 100% free. And thank you, Jackson. Jackson is in the Discord, which is also 100% free as well. All right, guys, thanks for that. We're gonna jump back into it and do another problem here. So I don't see the person that asked about resonance, but I do see King is still here. King, if you're still here, let me know, because I think you're up next, my friend. And then King basically asked about NMR. So I think I gotta skip the person that asked about resonance unless they pop up last minute, guys. That's how I do it here. Thank you, King. So, oh, Kenya. Oh, okay. So Kenya is here. Perfect. All right. So here's what we're gonna do. We're gonna do resonance for Kenya. Let me know if I'm saying your name correctly. And then we're gonna do NMR. Okay, guys. So resonance is something that is gonna be a little bit tricky the first time, but it's not too bad once you break it down. So the example I like to give for resonance, let me change the topic real quick, guys. The topic I like to give for resonance is benzene. Okay, so benzene, who knows the formula for benzene? Comment down the formula for benzene, the chemical formula for benzene here. Okay, and then so thank you. So this is going to be resonance. So benzene has how many double bonds? Okay, resonance is only for double bonds, by the way. Okay, so I need to have sp2 character, and so this is benzene. Perfect. This is going to be C6, not H12. It's going to be H6, right? Very close, King. It's going to be C6H6. Perfect. So benzene is going to be C6H6, and then we're going to do resonance. So what resonance does? Resonance moves electrons. Let's write that down, because as soon as you understand that, oh my gosh, it's going to start to make so much more sense. Resonance moves electrons. So we're going to take one of our double bonds. It doesn't matter if we do this one, or this one. I'm going to take one of my double bonds, Kania, and then I'm going to push it onto this carbon right over here. Okay, you see how I took my double bond and then I pushed it onto this carbon? That's going to create my first resonance structure. Guys, thank you for the love. Thank you for tapping the screen. You just hit 4.4K likes. All right, and then so what's that going to do? That's going to turn my double bond from a bond into a lone pair. So this doesn't change, but now I have a lone pair right over here onto this carbon. Is that making sense? So this one was my original benzene, and now I have my first resonance structure. But because I put a minus charge over here, what do I got to put on my carbon over here to balance that out? Okay, chat, if I have a minus charge over here, what do I got to put on my carbon over here to balance that out? Okay, this was the minus, and then what does that got to be over here? Okay, well, I can't have minus generated out of nothing, right? I gotta put a plus charge. Yasmin, welcome into the chat. There you go. Good job, King. Okay, so King said I have to put a plus charge in order to balance that out. Okay, next example, I'm gonna do that one more time, but this time I'm gonna sort of move my lone pair and push it, quote unquote, push it into this region here to create a double bond. Okay, but this double bond is now going to be occupied, so I also need to move this arrow over here as well. Okay, so now what am I going to have on this side? I encourage you to pause here and try to figure out what's going to be on the right hand side before I draw it. Okay, anyone that's taking OChem right now, if you're following along, I highly encourage you to don't watch this on your bed on your phone. I encourage you to actually take notes and engage. Okay, you're gonna get a lot more out of this. So try to draw out what's gonna be the product over here, and we'll draw that out together. Okay, so then we have this and then this. There you go. So BDR says lone pair for the electrons, and then don't worry, BDR, you're gonna be right after this. Actually, right after King. Sorry, so I added you to the list. It's gonna be minus right over here. And then, excuse me, sorry about that, chat. I put a double bond over here rather. There we go. And now my lone pair just looks like that. Okay, so what do you notice about this minus charge? Notice that it went from here to over here. So you might have heard your professor say that it skips a carbon, and it doesn't literally skip a carbon. It's moving over, but it looks like it skips a carbon. It went from here to over here. So your professor will probably say, hey Crystal, how's it going? Your professor will say that it skips a carbon. It doesn't actually skip a carbon. It looks like it skipped a carbon over. So let's see if that happens again. I'm gonna move this double bond over here now, and then move this double bond to create a lone pair over here. Beautiful. So now I'm gonna have this structure, and once again, I encourage you to pause here and think about what's gonna be over here. Guys, thank you for the love. We just hit 6.3K likes. All right, and then now what do I have over here? So now I see that this double bond didn't move. All right, I have a double bond over here, and then a lone pair just like that, and a positive charge over here, right? Making sense so far? We basically have our fourth resonance structure rather. Let me just clean this up a little bit. Okay, sometimes people ask me, does it matter if you put the double bond on the inside or the outside? It doesn't really matter, but it's better to have it on the inside just to be a little bit cleaner, a little bit neater, but it really doesn't matter from a chemistry perspective. All right, and let's repeat that process one more time. Once again, notice that it appeared to skip this carbon and jump over here. Okay, now we have a small problem, but it's not a problem because I can simply just put this lone pair back into the benzene ring over here, and then lo and behold, we are done. As a matter of fact, I don't even need to draw this one because we effectively have the rotated version of this guy. So notice that this one originally was diagonal down to the right, down to the left, and straight up. This one is now up to the right, down, straight up, and up to the left. So in other words, we have about 1, 2, 3 more resonance structures that I encourage you to try out on your own. Okay, does it skip the carbon all the time? Yes, that is actually a general rule that it quote unquote appears to skip the carbon. Okay, good question. And that happens for every single resonance structure, except in some rare occasions where you have some exceptions, of course, because you already know in chemistry there's tons of exceptions. So there's going to be a few more resonance structures that I want you to try out on your own. As a matter of fact, this is a good video topic that I should probably do. And guess what? You're going to get back to the original. Now, benzene is a special case because you don't always get back to the original. Oftentimes they go back and forth. Okay, you only have 2 or 3, but benzene, okay, C6H6 is a very, very special case where it does cycle in a, exactly, this is called a pi system. So for that reason, because it cycles, we often draw benzene not only with the lines, but sometimes professors like to draw benzene with the circle. What does the circle mean? The circle means that it repeats itself in a cycle of several different resonance structures. Okay, great question. Kania says, King says, would this work in a pi system? Yes, it would. Okay, this is called pi resonance because these are pi electrons. What do I mean by pi? I don't mean the number pi. I don't mean pi the food. I mean the pi electrons. sp2 pi electrons means double bond resonance. And then Kania asked a question that I get a lot, and I have to make a video about that, because Kania says, how do you know when to stop? Okay, I know how to do the first resonance structure, but how do I know when I'm supposed to end? Now, let me just do another example, and the short answer is basically formal charge. Okay, the short answer is formal charge. So let me give you one example of a carboxylic acid. Okay, it doesn't matter what I have on the right hand side, but let's say I have this. This is a deprotonated acetate ion, and I know I'm gonna have one resonance structure here, and then you might be like, all right, okay, I encourage you to take your time to think about, but I'm gonna reveal the answer just for the sake of time so we can move on to a different topic. I see I have my double bond over here and my lone pair over here. So I'm gonna take my electron lone pair and then feed it to create a double bond. But because I created a double bond, I gotta move this double bond and create a lone pair here. Okay, so now I'm gonna have what over here and what, okay? And then double bond, oh, just like that, okay? Just like that. So I know that I'm done. How do you know? Okay, I wish there was like a magic rule that tells you that I know, but the best answer is practice. When you practice, you're gonna just magically know. But the reason I know, okay, is because number one, practice, but it's also because where else can they go? My electrons are stuck. There's nowhere to go. It's like the end of the road. Okay, we got to the end of the road and my electrons have nowhere to go. So suppose I try to move them backwards, okay? And I try to do something like this. Well, guess what? I went back to where I originally was. So it's like, if you think you want to keep going, try it out. Try to keep pushing the electrons and you're going to see for yourself there's nowhere else to go because I already pushed them back. Does that make sense? Benzene circle figure. This seems interesting, meaning it do slightly more than just 3 bonds. Yeah, these are 3 double bonds, Isaac. Benzene is such a cool object of reality, such a trippy consequence of a resonance structure and moving electrons. And because of benzene, that's how we have electronics. You're going to find benzene in electronics. You're going to find benzene in pharmaceuticals. Benzene is in your brain. Benzene is in drugs. It's found in the body. Benzene is everywhere. Sometimes people say organic chemistry is the study of carbon, right? But I like to say organic chemistry is the study of benzene because benzene is everywhere. Okay? Anytime, Kania, hope that was helpful. King, let me know if you're still around. I'm going to cross off resonance for now and then move on to the next topic. And then we're going to cross off resonance, but I got to do a video ASAP on resonance because everyone always asks me that question. How do you know? Okay, thank you, King. So beautiful. The next question is going to be NMR from King and then BDR. I know you dropped a Discord question, so I'm going to tag you. If you're not here, I'm going to tag you because you're going to be up next. All right, so NMR and then quick question, King. Are you talking about proton NMR or carbon NMR? Are you asking about H NMR or C NMR? Because H is for hydrogen and C is for carbon. Whoa, Jackson, how did you do that? I don't know how Jackson did that. So NMR is going to be more about looking at the peaks and the figures. Okay. And guys, I have a really useful guide that I wrote over for NMR. Let me see if I can find it quickly. NMR. So guys, I have a Discord, free Discord. I'm gonna talk about it in a second. Hold on. NMR notes here. Let me try to find it. Jump to the message. Yes, I think I found it. Okay, perfect. I found my notes. So I have a free Discord community, guys, where I drop in free practice problems, review sessions, and cheat sheets and study guides. If you guys want that, just DM me for the link. And then Jackson, if you can vouch for me, that'd be perfect. No, I don't want good notes. I want yeah, good notes. Yeah, let me drag this in. So fortunately, I already did one for NMR. So King, if you want me to send this to you, just let me know. I'll send this to you. So guys, can you see that? Perfect. So we're gonna go over this, and I think for this one, I'm gonna temporarily get rid of my banner, and we're gonna go through this together. Okay, so NMR was one of those topics that I kept getting asked over and over and over again, so I went ahead and made these notes. So once again, they're totally free. So if you want me to send them, you can either join the Discord or just DM me and I'll send them to you. So we're gonna go through these together and just do a couple of these examples, and then also might talk a little bit about mass spec here. So Solomia, if you're still here about mass spec, we're gonna go over that soon. So NMR stands for nuclear magnetic resonance and uses radio frequency radiation to detect spin transitions in a magnetic field. So Isaac, this is gonna be your cup of tea, my friend, because this is straight up physics now. This is straight up physics. Yeah, I'm streaming on my iPad, bro. This is straight up on my iPad. Okay, we also have mass spec, which mass spec ionizes molecules to measure the mass to charge ratio of the fragments that are basically exploded off that particle. Okay, and both are powerful analytical tools for measuring molecular structure and composition. So the key features I want you to focus on are going to be chemical shift, integration, and coupling. So we're going to go through each of these one at a time. And so I highly encourage you to put on your chemistry cap and think like a scientist, guys. And what do I mean by that? Some of these terminology are very convoluted, but if we break it down with analogies, step-by-step examples, promise you it's gonna make a lot more sense. So proton NMR uses magnetic resonance to analyze hydrogen atoms, H atoms in a molecule. And so it's going to reveal the number, the type, and the so-called environment. Okay, they're going to call it environment. So once again, the key features are going to be the number of signals, okay, also known as distinct environments. Integration. What is integration, chat? What is the definition of integration or an integral in calculus? Okay, if you've taken calculus, what is an integral? Okay, in this context, it's going to calculate the relative number of protons, but someone please comment down below, what is the definition of an integral? Also, chemical shift, okay, which reflects the environment. And then finally, coupling, which is going to tell us about multiplets or neighbors. So what do I mean by neighbors? I mean literally, if we have a carbon next to several different neighbors, that's going to tell us in the peaks. Okay. So first we have chemical shifts. So what is a chemical shift? It's a proton position of an NMR signal on the delta scale. Indicates what's called a proton environment. What do I mean by proton environment? I mean literally, there's a proton right there. Imagine if your next door neighbor is a proton, okay? So what affects chemical shift is going to be electronegativity, hybridization, shielding, and de-shielding. So electronegativity is going to be based on the functional groups. I should add here, this is going to be based on functional groups. So some functional groups are highly electronegative, and some functional groups are electropositive, means that they're going to draw electrons and then push electrons away. Light emissions due to element transitions, there are spin differences. New physics is being discovered. Interesting. More phase states to consider. Quantum energy levels being discovered. Dude, that's crazy. Quantum is so cool. Okay. And so typical ranges. Let me just give you a table. Okay, so King, you're going to need this table, my friend. So you can either take a screenshot now or once again, drop it in the, I'll send it to you in your DMs. All right. So alkyl first, alkyl RCH3 is going to be 0.8 to 1.2. Alkyl RCH2, secondary alkyl is going to be 1.2 to 1.5 ppm. And then R3CH is going to be 1.4 to 1.8. Okay. So you pretty much have to memorize each of these, but don't worry, we're going to do a bunch of examples. So it's going to look something like this. Okay. So for all of these, we're going to read it from right to left. We're not going to read it from left to right. We're going to read it from right to left. Starting on the right-hand side, we start with 0 ppm. And then our first one are going to be our alkyl halides, primary, secondary, and tertiary. Sorry, our alkyl carbons, rather. Okay. And then we're going to have a bunch that live over here. Okay. And then the further we go down, what do you notice? The further we go down, they start to get larger in size. For instance, the benzene and the aryl. Okay. And then as we go down to the left, now we have highly electronegative constituents. Okay. All right, you got it, King. I'm gonna send it to you, but make sure you DM me, bro, so I can send it. Because if you don't DM me, I'm not gonna be able to DM you sometimes. TikTok TikTok doesn't allow sometimes people to DM me, so make sure you DM me and I'll send it to you. Okay, so let's see if we have this one here. Okay, I want to find some examples where the actual problem is given. Okay, let's do this one here. So based on the table, in what range would you expect to find the protons of acetone and ethanol? So some of your professors are really, really nice and they're going to give you the compound. And sometimes they're really, really not so nice. So they're going to, they may or may not give you the compound. So acetone, I'm just going to tell you right now, okay, because I'm nice. And then I'm going to draw C double bond O, carbon, CH3, CH3. So if your professors are nice, they're going to tell you this is acetone. If I'm not mistaken, that should be correct here. And ethanol. So ethanol is meth, eth, OH here. So we got to go to our table and identify what are the groups, what are the functional groups on this species, C double bond O. So I'm going to look for my C double bond O here. Okay, and I see I have ketone. Okay, so you see how I found ketone for acetone? That's about 2.1 to 2.6. Okay, 2.1 to 2.6. I also have my alkyl group 0.8 to 1.2. Okay, primary alkyl. And similarly for my ethyl, I'm also going to have a secondary 1.2 to 1.5. Okay, because I have CH2 and CH3. So I'm going to go back to my problem here and see if I'm right here. Okay, so I forgot my ethanol though. Okay, so I was right for my ketone. So for my ketone, I again have my 2.1 to 2.6 because this table that your professor is going to provide for you, or if you don't have one, once again, I'll send it to you. Okay, just DM me, is 2.1 to 2.6. So the correct answer here is 2.1 to 2.6. That's the range. Okay, and then for the alcohol, how do I know that something's an alcohol? Because ethanol is an alcohol, as indicated by OL for alcohol. That's going to be at 3.3 to 4.0. Okay, guys, so that's going to be the very first example for HNMR, and I hope that this is helpful so far. King, how are you feeling about this topic? Just want to do a quick check-in with the rest of our folks here. And pull back my list. Okay, so BDR, if you're still here, let me know, because I'm going to check your question in the Discord right now. This is for King right now. We're going over NMR. BDR, if you're still here, let me know. I'm going to check that Discord question right now. And then King, let me know if this is helpful so far. Okay, so once again, if you have any more questions, just DM me, my friend. I'm going to go ahead and move on to BDR. Let's see, pretty confident, explain it really well. Okay, anytime. So let me just do a quick overview of the rest of this, because you're going to see these have practice problems and peaks. So the next one you're going to go over is integration. So it's going to explain everything for integration. Okay, example for integration. And then it's going to tell you how to get these. Now, this problem, I did not add the solution here. So if you want me to drop the solution, just let me know. I'll make a video for that. Couple splitting. Now, couple splitting is kind of confusing the first time, but it's a very, very easy formula. It's just n plus 1. Okay, this is going to explain how to do that. Okay, so read up on this. It's going to explain how to do that. Okay, couple splitting, and then interpret NMR spectra. So here's an example of how to do that. And then a lot of these are over here as well. Okay, so go through. There's about 16 slides in there for you. The last one has about 1, 2, 3, 4, 5, 6, about 18 practice problems for you to try out. Okay, so I'm gonna send this to you right after the live stream. BDR, you're up next, my friend. As I promised, you're gonna check out the chemistry question. And guys, BDR is already in the Discord, so this is a perfect place for you to ask questions already, because he doesn't have to DM me or anything. He's already in. So that way it's a really easy way for me to see exactly what to go over. All right, beautiful. So this is going to be for chiral compounds. All right, beautiful. This is a great question. So, hi Elise, how's it going? Good to see you. I'm doing great. How are you doing? You can estimate ppm, it takes sense, but it's a ratio of resonance. So the total synthesis for chemistry is the most memorization of group functions, and it seems. A lot of OChem isn't memorization, it's like reactions. It's like understanding the reactions, yeah. Sounds like Marine Corps group rank. Oh my gosh, Faya, I literally just went over NMR, twin. If you want the notes, I was just going over this. If you want the notes, just DM me and I'm gonna send them to you after, okay? We just literally just went over this. But if you stick around, I'll be happy to go over it again, or I'll just send you the notes, okay? So this one says circle the chiral molecules among those below. Okay, so this one is gonna be open to debate. So I'm gonna put a circle right here. I'm gonna start off with the second one, just simply because I'm like a little bit lazy. What's going on? I can't drop a screenshot. I can't color this in. Okay, so can I? There we go. So I'm gonna do this one last, just because I'm like a little bit lazy. This one might be easier. I'm gonna do this one first. This one is also gonna be debatable. I'm gonna do this one second. Okay. So I'm going to start with this one. Right off the bat, I pretty much know this is chiral. Okay, right off the bat, I pretty much know this is chiral. How do I know that? Because a chiral, so what's the definition of a chiral compound? Okay. I forgot your name, but I know it's BDR. So BDR, what's the definition of a chiral compound? Guys, does anyone know what is the definition of anything that is chiral? It's basically going to be a carbon center with 4 unique R constituents, with 4 unique 1, 2, 3, 4 groups. Okay, 4 different bonds. Thank you, Kevin. Okay, and you said chiral center. Now that's using the definition. That's using the word in the definition. So you're not wrong. But what's the definition of a chiral center? Chiral center is going to be a carbon with 4 different R groups. Okay. So, like, every time I see a wedged versus a dashed, that's a really good indicator. That's like a check me. That's like screaming at me. It doesn't have to be chiral, but it's probably going to be chiral. It may be chiral. It's like a big hint. Okay. So I'm going to check my chlorine right over here. And I'm going to basically label all the constituents. I'm going to say this is going to be 1. Okay. I do have a methyl. Okay. I have a methyl. I'm going to just put a little asterisk right over here. I have a methyl. I have a R chain over here. And I also have a 4th group. Does everyone see the 4th group? What am I going to draw invisible right over here? My 4th group is going to be an invisible proton. Does everyone understand why I drew that invisible proton? Because of the octet rule. Okay? I need to have the H there to have 4 distinct groups, right? Thank you, Fire, for the follow. Exactly, right? Fire says H. Okay? So, therefore, I have 1, 2, 3, 4. So, yes, this is chiral. Okay? So, this is automatically chiral. Okay? So I'm gonna already circle this. Let's just double check with the second one, just in case. Just in case. Again, I have 1, 2, 3. You might say that's not chiral. Yes, it is, because we have an invisible H right over here. Okay. So it says circle the chiral molecules among those below. Yes, I'm gonna circle this one. Okay. So that one is certainly chiral. Okay. So you got +2 already. You got +2. I'm gonna skip this one for now, just because I'm like a little bit lazy. But we're gonna take a look at it in a second. This one is a little bit sus. I want to say not chiral, but I'm going to do it in a second here. Okay, what about this one? So this is going to be a Newman projection. So Newman projection means we have carbon in the center here. And then we have carbon on the center here. Now, I'm tempted to say yes, chiral. I'm tempted to say yes, chiral, because what if I draw it out? Okay, this one's a trap. I got to be really careful with this one here, guys. I'm going to draw my Newman projection. This carbon means that I'm going to have a line just like that. I'm going to have an ethyl just like that. I'm going to have an OH that is wedged. And then a proton. Excuse me. This one is going to be, my OH is going to be dashed. My proton is going to be wedged. I'm going to have my ethyl just like that. and then I'm gonna have my OH, which is wedge. Now, this one's a trap, BDR. This one's a trap because it looks like it's chiral. We gotta be really careful. So does it matter if there are two centers? Pretty much CB, you're saying, pretty much because you're saying if there's one center, the whole molecule is chiral. Yes, but be careful with this one, right? Be careful with this one. I see that I have 1, 2, 3, 4, okay? So in other words, I have carbon attached to H, OH, ethyl, and then I'm gonna call this entire thing R. I'm gonna call this entire orange group R. Okay? So this entire thing, I'm gonna call it R. Ooh, that is a trap. I almost fell for this one, chat. This one is a trap. But, so you might say, oh, this is 4 unique chiral centers. Okay? And it's sp3. But, what if I draw the right-hand side? The right-hand side, I'm going to draw my carbon center. And then I'm going to draw another ethyl. Okay? I'm going to draw an OH here. And an H over here. And another ethyl here. So, but this is now going to be my R group. So this R group is going to be this thing here in green. Aha. But is this R equal to this R? They are the same. So this one is actually meso. This is a good example of meso. This is achiral. Achiral means that, yeah, it looks like a chiral center, but this carbon is attached to this R group, but this orange R is the same as this green R, so we are not going to circle that one. That one is that's a trap. I love that one. That's a good one. Make sure you study that one. Let me know if that one made sense. Okay, so we're not going to circle that one, so we got another +2. Got +2, we got +4. Does that make sense? That one's a trap. No resonance is happening. If you have resonance, automatically means chiral. I mean, resonance means not chiral. So all of these have to be single bonds only, no double bonds. If you see double bonds, eliminate it. It's not a chiral center. It could have double bond. Now, it could have double bond and a chiral center. Okay? But if you see a double bond, it's not a chiral center. Hopefully that made sense. Okay? You could still have double bond and still have a chiral compound. All right. Now let's do this one here. So, I'm going to eliminate all of these ones here. I was thinking anti was chiral and gauche was chiral. No, anti and gauche don't have anything to do with chirality. That's just the orientation. Yeah, that's all right. You were thinking anti versus gauche. Right now this is anti. Okay, but that has nothing. That's not going to tell you any information about chirality. For chirality, we have to follow. Think of chirality as the formula. The formula has to be all sp3. Okay, 4 unique carbons. Okay, that's the formula. sp3, 4 unique carbons. Okay, let's check this one. So I'm going to eliminate this and this and this because those are not chiral centers. So right now my brain wants to go to right over here. So I'm going to put an asterisk right over here and right over here. So in my brain, okay, right now I'm drawing it out so you guys can see it, but ideally for your exam, you gotta be quick with it. So in my brain, I'm gonna draw this one. I'm gonna put carbon, I'm gonna put OH, I'm gonna put H, I'm gonna put R1, I'm gonna put R2. So R1 is gonna be this entire thing on the right. 1, 2, 3 here. Okay, I'm gonna highlight this one as well. R2 is this thing on the left. So this one's R2 and this one's R1. Okay, so far this might be chiral, but I'm concerned it might be meso. So far I'm concerned it might be meso. If it's going to be meso, then this one is going to be the same thing here as well. So what about this one here? So this one is a carbon. So far it could be chiral. I gotta just double check. And now I'm going to draw my OH here. And then I'm going to do another R1 and another R2. Uh-oh. That's a little concerning because now I see I have R1 and R2. Okay. So my R1 is going to be this guy. Okay, but my R2 is going to be this guy. But, okay, this time my R1 is going to the left and my R1 is going to the right. So this is kind of hard to explain, but my R1 is actually going to the right, kind of. How do I explain that? It's kind of hard to explain. I want to say this isn't because OH are both wedge and you have a line of symmetry. Yeah, you do have a line of symmetry. Actually, you don't have a line of symmetry, I don't think. Wait, is there an internal mirror plane? This one's tricky. This one's tricky. No, I don't see a plane of symmetry here because this one is going up and then H is going down, so I can't like cut it in half. Does that make sense? So this one is 2 carbons to the right. In other words, okay, I think I found an easy way to explain it. This carbon here, this one, I'm going to highlight this one in, let's say, orange. This carbon, my ones to the right, I have two C's here. 2 lone carbons. 2 lone carbons. 1 lone carbon to the left. Okay? But this one, because that's this one here, I'm going to highlight this one in, let's say, blue. My one to the right of here, which is my R1, that's to the right. I only have 1 lone carbon. Okay, so that's why it's not symmetrical. 1 lone carbon, and then I have 2 lone carbons. So they kind of flipped. So yes, this is chiral. Okay? We got 3 out of 4. I know this one's kind of tricky. All right? I'm gonna take a screenshot of this and then drop it into Discord and tag you. Okay? So the reason this one's chiral is because this carbon here, if I look to the right of here, I have 2 lone carbons. And then if I look to the left, I have 1 lone carbon. So those are unique R groups. Yes, chiral. And then this carbon here, if I look to the right, but I'm pointing to the left, you're saying, hey, Dr. Drew, you said right, but you're pointing left. I know, but I'm putting it like around. I'm moving it like around in my brain. So it's like if I like rotate around it, now relative to us, the viewer, yes, this is to the left, but relative to this, I'm actually to the right. So this one to the right is only 1 lone carbon. And then this one to the left is 2 lone carbons. And you're saying again, hey, but you're saying to the right, but you're pointing left. And you're saying to the left, but you're pointing right. I know, because I'm rotating it around. Gosh, I hope that makes sense. I know that's super tricky. It's a rotating thing in your brain. You have to like rotate it in your brain, kind of. Okay? This is called spatial awareness, chat. This is called spatial awareness. If you're good at solving Rubik's Cubes, that's going to help for organic chemistry. It's kind of like solving a Rubik's Cube. So far we circled 2, and then we eliminated this one. Okay, last one I have is here. Last one I have is here. So now I have these ones, and I'm going to cross out the ones that I know are not chiral. That's this one, that's this one, that's this one. Why did I cross off this one, chat? Okay, how do I know this one's not chiral right off the bat? I know this one's not chiral because I have methyl and methyl. Those are identical, so that's not chiral. What's tricking me isn't viewing it per se, but rather getting into the deep detention down, like if it's symmetrical, if it's chiral, and unsymmetrical chiral. Yeah, exactly. If it's symmetrical and chiral, it's called meso. Okay? Think about meso. I kind of think of like meso as like a taco. What do I mean by taco? I mean like not like a taco, like a... I need to think of a good analogy for meso. Meso means that it's chiral, but it's symmetrical. So technically it's achiral. Okay? So you're saying, okay, you're good at the spatial awareness stuff, but you're confused about meso, I think. Okay? So you're confused about like the meso stuff. This one was meso. Meso means that we have two chiral centers that have a point of symmetry. All right. So this one's not chiral, this one's not chiral. So I'm looking at this one and this one. So right off the bat, I'm a little bit concerned again for the same reason. I'm going to number my carbons. I see I have R1. I have R2. I'm going to color all this in R2. And I'm going to color all this in R3 in purple. Okay. So I basically have carbon, R1, that's in blue. And then I have R2, that's in green. Don't forget my H. And then I have R3. Okay, so potentially this is chiral. Potentially this is chiral because I have my R1, R2, I have my H here in red, and I have my R3 in purple. Okay? So potentially this is chiral, but I gotta be really careful, and I have to draw this one now. Okay? So that's gonna be this one here. I don't see any chiral centers here. Let me see. There's gonna be 1, 2, 3. Yeah, I still have my H there. Okay. I'm not sure, chat. I'm not sure. How do we feel about this one? I think it might be chiral. This one. Okay. I'm still debating about. Guys, I'm open to debate. I'm open to discussion. That one's a good one too. What about my other one here? I have 1 CH2, 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 and another H down over here. Okay, so I'm gonna color this one as R1. I'm gonna color this side as R2. Let's say R3. And then this one's gonna be R2. I'm gonna say this one is chiral. Wait, but this one is CH3. Oh, wait a sec. This is CH3. And then I'm 1, 2 away from that one. And then I'm 1, 2, 3 away. And then 1, 2, 3 away from that. Okay, so you're talking about axial versus equatorial, right? So it's the center within axial and equatorial chiral center. Yes, this one here. No, this one is not chiral. This one is not chiral because this one is not unique because we have CH3 and CH3. So CH3 is the same as CH3, so we're going to eliminate that one. So that one is not a chiral center. I'm considering this one and this one. Okay. I think this is chiral. I think this is chiral because we have R2 is not the same as this R2. And this R1, yeah, these are the same. But this one is 1, 2 away from this dimethyl. And this one is 1, 2, 3 away from this dimethyl. So yeah, this one's actually chiral, I think. This one's I'm pretty sure this one's chiral as well. I'm open to discussion on this one. So I see 2 chiral centers here, this one and this one. So I'm gonna say, yeah, this is chiral. So for my final answer, I circled this one, and this one. But I'm open to discussion on this third one. Is a little bit tricky. Okay? Yeah. But I'm pretty sure this one's chiral because this R group to the right is not the same as this R group to the left. Chirality is importantly mainly for what? Okay. There's two answers to that question. One of them is yes, the properties, and the other one is that chirality is more of like a naming thing. But if you've seen Breaking Bad, you know that Walter White talks about. All right, bro. Have a good evening. Breaking Bad talks about how there's two isomers of the same compound. One of them cures, if I'm not mistaken, one of them cures like something for pregnant women. I think it like treats some kind of thing for pregnant women that they get something if you're pregnant. So it's a good thing. It's a drug. But if you have the opposite version of it, let's say that one's R. But if you have S, you have meth. Okay? So the reason chirality is important is because on one hand, if you have the left-hand side version of the drug, it's a good drug. And if you have the right-hand side, you have an addictive drug. Yeah. Yeah. BDR, let me know if that was helpful. I'm open to discussion on the third one, but that's what I got. Guys, thank you for 31K likes. This is a really fun stream for me. And let me just drop this in so you can take a screenshot and open to discussion here. Open to discussion for number 3. All right. Next one I'm going to do, guys, I'm going to jump to Gen Chem. I'm going to jump to Gen Chem. I got a Gen Chem request here. And guys, we're going to see what this is all about. I think this has to do with quantum stuff. So we're going to take a look at quantum stuff. Chirality is crazy, higher synthesis chemistry rules. And guys, one more quick little chime in. Wait, let me just do one quick little chime in. Guys, if you want to sign up for tutoring, I got you for Math, Gen Chem, OChem, Physics. Go to engineerminds.co, sign up for a free session. Okay, first session is 100% free. All right, tap that link in bio if you want to sign up, and visit engineerminds.co if you want to join the Discord for 100% free. Check out free resources for Math, Gen Chem, OChem, Physics, and guys, check it out. So if you tap that link in bio, engineerminds.co, tap this link that says join the Discord, you get connected with like-minded students, make new friends, access to free resources, study tips, and tutoring discounts. So just visit engineerminds.co if you want to get that link, guys. And check out the resources page, guys. I'm trying to build out. We have 6 practice problems for Gen Chem, 3 study guides, and we got 2 interactive sections for biology, 8 interactive for engineering, and we got 5 practice problems for physics as well. So once again, that's engineerminds.co for all that good stuff. All right, guys. So here's that one for Gen Chem. Let's take a look. I've heard that all bachelor chemistry students can cook if they were competent, but PhDs and masters chemistry can do chirality and specific synthesis. Yeah, I wouldn't know because I'm not a guys. I'm an engineer. Technically I'm an inorganic chemist. Technically I'm not an organic chemist because my background is in photocatalysis. So organic chemistry is like my secondary, guys. I'm not gonna lie about that. Okay, but I am really good at teaching it though, so that's the thing. So this is now Gen Chem, guys. Switching gears here. Rank the following 3 transitions in the hydrogen atom in terms of lowest to highest energy levels. Lowest to highest energy levels. Frequency, wavelength 8 to 5, 6 to 4, 3 to 1. What are the options here? It just says energy, frequency, wavelength, and then it just says choose. My high school AP chemistry teacher had a PhD. Ooh, interesting. Let me ask them, what are the options? What are the options when you say choose? So I know we're raking the photon energy for 3 H atoms. Make this bigger one more time. Guys, I'm gonna try, I might ask for your help here, guys. I'm not sure what is this really asking. It just says rank the following 3 transitions in the hydrogen atom in terms of lowest to highest energy, frequency, and wavelength. 8 to 5. Okay. 8 to 5, 6 to 4, and 3 to 1. I'm just trying to figure out what the heck this is asking. Okay. Okay, I think I know what it's asking. So it's saying 8 to 5, 8 to 5, 6 to 4, 3 to 1. Okay, so this is going to be 8 to 5, 6 to 4, 3 to 1. So we're going to use the... We're going to get the relative... All right, I think I got it. I think I got it. So let me do this one more time. Let me pause the music. I'm going to kind of lock in. I might record it. I might just turn this into a TikTok. So let me just pause the music, lock in for a sec. Okay, let me lock in for this. I'm gonna basically do a live TikTok recording here. Okay. Okay, I think I understand. I just want to just lock in for a sec, guys. I think I understand here. So this was a live stream. I'm gonna turn this into an impromptu live TikTok. So this is, you guys are gonna watch me live how I record a TikTok. And I'm gonna just download this and turn this into a TikTok later. Okay. Okay. So it says, rank the following 3 transitions in the hydrogen atom in terms of lowest to highest energy, frequency, and wavelength. So we have 8 to 5, 6 to 4, and 3 to 1. And we have this table here, and it says energy, choose, frequency, wavelength, choose, and it says lowest, medium, and highest. Okay, so first things first, I'm gonna write down these transitions. So first one I have is 8 to 5. Transition from 8 to 5. So the equation I'm going to use is basically the Rydberg formula. It's given by delta E equals (13.6 eV) times 1 over n2 squared minus 1 over n1 squared. Okay, so here is going to be my constant, 13.6. All right. And I also need to know the formula for wavelength and light. E is equal to h times nu, and nu is my frequency, c over lambda. Okay, but h is a constant. So first things first, I gotta calculate my relative energies based on these transitions. Okay, so I'm gonna compute for 8 to 5, delta E equals 13.6 times 1 over 5 squared minus 1 over 8 squared. Okay? And a 5 squared is a 25, so this is going to be 13.6 times 1 over 25 minus 1 over 64. And I'm gonna just compute that. Five squared, 13.6 times 1 over 5 squared, minus 1 over 8 squared. So I'm gonna get 0.3315. So I'm gonna say delta E, 8 to 5, is 0.3315 EV. Okay, so I'm gonna go to my, okay, I'm gonna just box that for now. I'm gonna see what that is. I'm gonna repeat that process for my next frequency, 6 to 4. So I'm gonna plug in the same numbers, but this time I'm gonna use 6 to 4. So I'm gonna say my delta E is 13.6 times 1 over 4 squared minus 1 over 6 squared. So this time, I'm going to get delta E equals whoa, that's trippy, guys. Do you guys see that? Whoa, that's weird. I don't see this on my iPad. I only see it on my screen. That's weird. That's so trippy. Let me try to hide that for a sec. Was that covering up before? I didn't notice that. It's not going away. Okay, I'm just going to go down here and repeat that one more time. So now I'm going to repeat that one more time for transition from 6 to 4. So I'm going to use delta E equals my 13.6 times 1 over 4 squared minus 1 over 6 squared. Okay, so this time if I compute that out, I should get delta E 6 to 4 equals 0.4722. 0.4722 EV. And then finally, I'm going to repeat that process one more time from 3 to 1. So I'm going to say delta E from 3 to 1. One more time, it's going to be 13.6 times 1 over 1 squared, which is just 1, minus 1 over 3 squared, which is 9. And then plug these values in. 3 squared. And then this time I'm going to get 12.088. EV. Okay, so let's put this in a nice table so we can see what we got. I'm going to say our 3 transitions were from 8 to 5, 6 to 4, and 3 to 1. And so for our delta energies, we got 12.08, we got 0.4722, and then we got from 8 to 5, what was that again? 0.3315. Okay, so we can see that the highest energy is from 3 to 1. This is the highest energy. This is medium, and this is the lowest. Okay, what about wavelength? But wavelength is inversely proportional to energy. So I'm going to do the opposite case. If this was the highest energy, I'm going to have the smallest wavelength. And then this is going to be the medium wavelength, and then this is going to be the largest wavelength. Okay? And frequency is also going to be in the same order as energy. So our final answer should be this table that we have here. Okay? And beautiful. So guys, I think that was my first time doing a, like, I'm going to clip that. I think I should be able to easily like cut it and clip it and then post it tonight. Huh? All right. Awesome, guys. We got 30 minutes left on the clock today. I don't see too many other questions. Everyone else that joined in that asked questions earlier, I'm assuming they're gone. For example, I got one question from my Instagram. I'm going to check that in. I'm going to take a look at that. And let's see, you got a request here. So Solomia, I don't know if you're still here, but we're going to take a look at it here anyway. And it says, which of the following gives rise to a prominent peak in the mass spectrum with MZ of 91? Guys, I don't know if I'm able to answer this. This is kind of a weird question. So here's what, so a good thing I took a screenshot of it, and then I asked her to send me what are the options. So guys, that's the question that Solomia dropped. And then the options here are 1 octene. And then this is 1 hexanene. And then we have benzene. And then we have ethylbenzene. Guys, I'm not sure. This is kind of like a weird one for me. CH2, CH2, CH2. Okay, I'm not even going to draw all that. I'm just going to draw this out. CH3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Amine. NH2, 1, 2, 3, 4, 5, 6. So here's the question. As you can see on the top, it says, which of the following give rise to a prominent peak in the mass spectrum with mass to Z of 91? Yeah, sorry, I'm just bringing that back. Sorry. I'm bringing that back now. Okay, so wait, I think I know what it's asking now. So by the way, this is C6H6. What is what is 1 octene? Okay, I'm going to kind of cheat. I'm going to look up what are these compounds because this is homework, not a test. So I'm assuming she has access to the internet. I'm going to message her. So 1 octene is basically this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 octene. Hexylamine benzene. And then ethylbenzene. I feel like I should know what is ethylbenzene, but I feel like I haven't heard of it. Yo, Rog. Ethylbenzene. Okay, it's literally just a benzene with an ethyl, duh. Ethylbenzene, just like that. Okay, so I'm also gonna cheat. I'm gonna look up I don't have to look up the energy levels. It's just mass. So I'm gonna look up the masses of these. I'm just gonna look up the masses of these. Yes, I can calculate it using GenChem logic, but I'm gonna kind of cheat. I'm just gonna look it up. I can calculate it using the molecular weights, but I'm kind of a little bit lazy. Not lazy, but like, yeah, I just don't feel like doing that. Let's just say lazy. So this is 106. Okay, I think I know what it's asking now. 101, 6.67 grams per mole. And then benzene is 6 times 12. 12, 24, 36, 48, 62 plus 6. Is that 78? And then she circled ethyl benzene. I don't know if that's right or wrong. I'm trying to just figure out what the heck this problem is even asking. I think I know what it's asking. Yeah, this is 78 grams per mole. 1 hexylamine. I think I know what it's asking, guys. She circled D. I think I know why it's D. Because it asks for what? It asks for which of them can basically explode 91. So what is 106 minus 91? And then what is C2H? 1, 2, 1, 2, 3, 4, 5. C2H5. This is going to be 12 times 4. No, 12 times 2 plus 5. That's 24 plus 5. 24 plus 5 is 29. So what is 106 minus 91? 106 minus 91. 106 minus 91. The only thing is, like, I'm having a hard time explaining it. I just know that we're going to explode off. We're going to basically, because mass spec is basically like literally destroying the compounds. So we're going to explode this. Oh, this is 15. This is 15. I thought that was going to be 29. Okay, we can eliminate benzene. We can't do jack to benzene. Okay. We need to figure out which of these can basically pop off a compound that has a molecular weight of 91. Yeah, mass to charge ratio means that its mass to charge is basically as mass is 91. Okay. I'm doing a really bad explaining this, but I'm just trying to figure it out myself. This problem is freaking weird, guys. We know it's not benzene because benzene can't really... It's not going to break off anything. Let me see which of these molecules, like... Let me get the rest of these. Guys, can someone look up what is the molecular weight of 1 hexamine? And I'm going to look up the molecular weight of 1 octene. Someone look up what is 1 hexanamine. I'm going to look up 1 octene. This is getting annoying, I'm not gonna lie. I'm trying not to like yawn, but I'm gonna start yawning, guys. 1 octene. This one is 112. Okay, that's promising. 112.24 grams per mole. Yeah, we know it can't be benzene because that's less than that, so it's already off the bat. Hexanamine. And then this is 101. Okay, I think it's gonna be hexanamine. 101.19. And then what is NH2? NH2 is 14 plus 2, which is 16. So what is 101 minus 16? If 101 minus 16 is 91, then we're solid, which it's not. Okay, that's 85. Shoot. What about minus CH2? What about minus CH2? So what is 112 minus 12 plus 2, which is 14? So what is 112 minus 14? That's 98. I think she circled D, guys, and I think it's D. But how do I... Wait, what is benzene again? That's 78. Oh, what if I just take off the... Oh, wait a second. What if I don't take off the whole thing? What if I just get rid of that one? So what is 106 minus a CH3, which is CH3 is a 12 plus 3, which is a 15. So 106 minus 15, is that too big still too? 106 minus 15. Yeah, 91. Yeah, it's ethyl benzene. It's ethyl benzene. So what I did, guys, here's the answer. Now I can explain it. So we have ethyl benzene. Boom, 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 boom. So I have ethyl. Okay, first I took off the whole thing. That was too much. So then I took off only this part. I basically exploded it using mass spec. I said the whole thing is 106, 106, and then this part is a CH3. So CH3 is a 12 plus 3 equals 15. So 106 minus 15 equals 91. So that's why the answer is ethyl benzene. Beautiful. All right, guys. Yeah, it's kind of like process of elimination, but like, in a way, that's like a pun, Jackson, because it's like process of like eliminating the constituents. Mass spec is like you're literally destroying the compound to visualize it. Mass spec is like what's a good analogy? Mass spec is like you're like trying to figure something out by destroying it. That's what it is. Like, what's a good analogy? What's something that you like when you try to figure something out by like destroying it? Like, I don't know. You're trying to look at the evidence, but you're destroying the evidence. All right, guys. I'm gonna take a screenshot of that and then send that to that person. And guys, I'm gonna try my hardest to get these videos out tonight. People are asking about these tonight. All right, guys. Let's end it here. This is a fun stream for me. Got some more peeps in the chat. Finally, school's picking it up. School's picking up again. And yeah, guys. This is making me miss school low-key. This is making me low-key miss school, guys. So we got the resources. We got 44,000 likes today. We got 5 new follows, 181 views. Really appreciate all's interaction and all support. I think we peaked at like 20 viewers today. And yeah, guys. So you already know, whoever's still here, it shows 0 viewers, but I think there's still viewers. So you already know, book a free call. Go to engineeringminds.co. Yeah, destructive analysis. But is there like, what's like a funny analogy? Is it like when your kids, like if you're like a parent and your kids are like, I don't know. I bet there's a funny analogy for like mass spec. Destructive analysis is the correct. Yeah. Smashing a fossil to carbon date it. Exactly, yeah. I guess that's like a perfect analogy. Smashing a fossil to carbon date it. But I was trying to think of a funnier analogy. All right, guys. Gonna end it for today. I'm gonna be back tomorrow, 5 o'clock PST. I might be on earlier. I'm gonna try to go on in the morning as well, just because I have more time right now. And yeah, guys, visit engineeringminds.co. I got you for your first free OChem session. We got Gen Chem Math, OChem Physics, and Engineering. I've helped a number of students that were feeling lost and confused with OChem and Gen Chem. And now they feel really confident, guys. I'm gonna help you get situated, feel ready to get back on track. I'm gonna explain every single topic step by step, and help you feel confident, ready for the final. All right. I did not see that. I'm gonna check it out right now. And yeah, guys, just gonna hang out here. Any more last minute questions, any more last minute inquiries, feel free to let me know now. Forever hold your peace. Otherwise, guys, I'm gonna start editing these videos. I'm gonna try to get them out tonight. And yeah, peace out, my friends. Have a great rest of your evening. Deuces.